That's fascinating. I think I might have had 3 OBSs open. Bienvenue, welcome to rocky start of a stream. Yeah, I think it's going now. So, willkommen, bienvenue, and welcome to Coding Stuff Live with Light. Yeah, that was a weird start. I apparently had 3 OBSs open instead of 2. Caused some trouble. Okay, now everything seems to be live. Brilliant. Let's ping the Discord. And there we go. Let's get the music going. Move the game. Turn up sound. There we go. Okay. And today we're gonna actually start a new filter. Like, we're not just going to add to our good old-fashioned filters.shader. We're gonna start something brand new that does something distinctly separable from the other filters that I made. Like, I probably wouldn't want to just have this around all the time, and if I want it, I can just add it. Hey there, Win! So what we're gonna do today is quantization and dithering, which back in the day was something they did because they had to. Like, quantization was a problem and they solved it with dithering. I'm gonna try to do it to evoke a particular effect. So yeah, we'll see how it goes. Step 1, I'm going to duplicate filters.shader, filed under F. Okay, so I have not seen Return of the Obra Dinn. I've heard that it's good, but I also heard that you shouldn't watch it if you want to play it, and so I have avoided watching it. Okay, so we're gonna start, because my idea requires several filters to get the job done. And so we're gonna start with, ooh, I should give them all a prefix such that they stay together. I'm gonna call it qd.squash.shader. Such that all of the QD filters stay together. Oh, it has a cool dithering effect. Neat. Okay, so we're gonna get rid of the uniforms. We'll keep fract, we'll chuck rand, because there's nothing random about this. Norm, do we need norm? I don't think we need norm. We do need RGB to HCU and HCU to RGB. Okay, and then we've got this main area which does all of our stuff from the other filter, but we're gonna change that. Dim-san, welcome back. Right, so all of this can go because we're not doing any of this anymore. And so we'll just return C, save it, and then let's move OBS over onto my other monitor. And we will turn off the spoopy filter. And then we will activate our new filter, which we're going to call Squash. And you can shift them around. That's good. Load from file. Browse for file. Cutie Squash. Load. Hey, it didn't break. That's always step one, is thank goodness it didn't break. Let's make sure that it is in fact active. And so what we're going to do is return C over 2. This might not seem like much, but it's enough to make sure it is running properly. And there we are. So it cut the alpha in half as well. I'm not sure that's a problem. We're just making sure that it is running. Cutting it in half is part of the squashing, but we're gonna squash it differently. Because what we really want is the RGB to HCU squashed. Again, squashing the alpha. I don't think it's necessary, but I'm not sure we have to go out of our way to avoid it. Because we're always just going to return a full alpha image anyway. So we'll save that. We will reload the effect. And now it looks really weird, but that's because it's in an improper space. It looks kind of fun, though. Let's see that in all its glory. That looks really neat. Is everyone here a programmer or something? I don't know. There aren't a whole lot of people here. So the answer is maybe. But if there's anything you don't understand, feel free to ask. I am always happy to teach as I'm coding. But yeah, this looks really cool. When you change the space, it just makes it a different sort of thing. Because the blue is how bright it is. And so the whites will be blue. And anything that doesn't have any blue in it is dark. Manuel, welcome back. Okay, so yeah, this is not our end product. This is just the initial squashing. Hey, ask what I'm doing. It'll create more questions, and then I'll answer those questions too. So the first thing that I'm doing is squashing this space. So instead of taking up the area from 0 to 1, it's taking up the space from 0 to 1/2, which means I can fill the other half of the space with other information without really losing much about the original image. That's the first step, because in the middle, I'm going to be doing various things that need the original image and more information, and I want to carry that along as it goes. And then at the end, I will combine the two to get back to normal. But this is the entirety of my squash filter. Like, this is all I wanted it to do. So now we need the thing that turns it back. So I'm going to copy squash. And I'm going to make something called unsquash. So qd unsquash.shader. So these functions, RGB to HCU, RGB is the standard from goodness knows when for how monitors output light, red, green, and blue. And that's because it's easy to do, that you can have individual little elements of each of the colors, and you can make any color using those three. But they're not necessarily perceptually meaningful to us humans. Yes, we are all humans here. But I'm converting it to what I'm calling HCU. I'm not sure what the canonic name for this is, but it's hue, chroma, and luma. So the luma is how bright you think something is based on how the colors are distributed. RGB was first used in 1861. Thank you, Avena. People are full of useful information. So this is how bright it seems to you based on the color content. So the red has less of an impact than the green, which has tons, and the blue hardly has any. And so we convert that to get to the luma for how bright it is. The chroma is how colorful it seems. So a chroma of 0 is gray. Chroma of 1 is the color that you think of when you think of a color. And then the hue is an angle from 0 to 360. I normalize it down to 1 for the wheel of color. There's no true starting point. Well, there is. I mean, physically speaking, there is a color with the shortest wavelength versus the longest wavelength, but the way that we work with color and the interference that leads to our impression of color, it goes all the way back around. And in our experience, it's round, even though phenomenologically, it isn't. That's really fun. But we need to unsquash this. So we're getting a color in which is going to be in the HCU space. And so we need to change it back. But it's two things in the HCU space. It's both the color and the distributed error, because we're going to do a error propagation, error distribution, error something, dither algorithm. And so we need to propagate some errors, and we need to store both the original image and the error. And so we need to separate those two things, and then combine them, and then unsquash them. And oh, that's the other thing. That not only do I need to separate them and unsquash them, I need to find the color in our palette that is closest to them. But step one will be separate and unsquash. So we have a squashed color coming in. What we need to do is take that color. I'm gonna leave the base color there and put it in something new. We're gonna call it U for unsquashed equals C times 2. Okay, so it's 0 to 1, the bottom half taken up by one of them, the top half taken by the other. And so by multiplying it by 2, we now have something between 0 and 2. Between 0 and 1 is one of them. Good to go, ish. And then the top half is problematic. Is that how it's going to work? Yeah, because we've got the fractional part and the non-fractional part. And so float for E equals. So the error is going to be on top. So this is going float 3, really? We actually might want it to be a float 3, because we're never going to be doing anything with the alpha. No sense doing math on things that are never going to change. Okay, so now how do we do a GLSL floor? I mean, floor should just be a function, yeah? Because we should have used it up here. Yeah. So we have floor and fract. GLSL, it is the shader language for OpenGL. GL being graphics language, I think. So that's the language that we're writing in right now. So it's probably cheaper to get the fract and then subtract it from the whole. So let's do this. Let's just try that swizzle first. Make sure it doesn't break anything. So we're gonna add unsquash to our filter list. I know you can't see this, but it's going on. Okay, unsquash has not broken it. That's always an important thing to check, is that we didn't break it. Okay, so float 3 of E. Actually, no. Because we're going to get the fract first. The fract is the pure. And so what we want is U dot is the floor. No, the fract of that. Why'd you say that twice, Pretzel? Now, this would probably be better if this function were overloaded to handle float 3s. So I'm going to test this first and then see if I can overload functions. Because that's an important thing to know. Do I plan on doing more drawing streams? I would like to do more in the future, but they won't be nearly as frequent. Now that October is pretty much over. Hey, it worked. I still want to do them now and then when I have ideas and time and inclination, but I do want to get back to playing games. Okay, so now let's try to overload this function. Let's make a float 3 fract that takes a float 3 x. And so what we're going to do is return a float 3 of fract of x sub x, fract of x sub y, and fract of x sub z. So we save that, and we reload the effect. Oh, it didn't crash. Love when things don't crash. So now we should be able to just do fract of u. Hey, it didn't crash. I love when things don't crash. Okay, let's make sure that it's running and can crash. And it can. Good. So, we don't have any particular guarantee that it's doing exactly what we want it to be doing. But it seems to be working. So what we're going to do is return... Actually, just P. We're going to return the pure image and see what we get. Oh no, it broke. Because it needs a float 4. Oh! So close. So it's not exactly working. So now we need to figure out which part of it broke. Oh, the fact that we didn't convert it back. But it should still be showing us the HCU version. That's not good. So whatever happened with P, it's not coming through the way it should. So we'll still try. But I'm pretty sure this is not going to be... Yeah, it's not right. So the question becomes, is it this overloaded fract? Let's comment out this fract. It sure is. Okay, so the overloaded fract did not function the way it was supposed to. I don't know if it disliked being X. Hey there, Mac. You haven't missed too much. I made a squash filter, and now I'm making an unsquash filter. Okay, so we save this and reload. Should not have changed anything. Comment that. U is already an XYZ, so we should be able to just do that. And then what do we get? Something weird. Because we definitely pass in a float 3, which means it should send it here. which does the same exact thing as what I wrote here. That's super weird. But that's okay. We don't need to use the overloaded version. We can just use it as it is. And so that's the raw image. So this is with no filters. This is after it's been squashed and unsquashed. I don't really see a difference. So it makes me think that the bit depth of the image is way deeper than Stardew Valley requires. And so we can squash it in half, which really only removes 1 bit worth of depth. And we lose nothing. So we can store all of our extra information in the other half that it doesn't even need. So that's pretty cool. So that's the pure image extracted. And now we need the error extracted. And so the error is u minus p. Over 2. So that's the part between 1 and 2, I think. Wait. So this would be the part between 1 and 2. So that's not what we need. Not exactly what we need. We need to subtract 1/2 from it. Yeah, like Stardew itself doesn't use that many bits. Okay, so space is between 1 and 2, which is exactly the size that we want, but it's too high. So we just subtract 1 from it. Okay. And just to be certain that it is what I think it should be, we're going to return E, which should be black. Oh, is broken. Float 3, float 3. Can we not subtract 1? Probably not. Oh, we cannot display a float 3. Black. There we are. Well, it was less than black, actually. It was transparent. Okay, so the error is black, which is what it was supposed to be. Because we haven't, actually computed any errors yet. That's not the job of the squash or the unsquash. That will be the job of the propagator in the middle. So now we've got the pure image, we've got the error. And so what we want is the color in our palette closest to the sum of those. Now, I don't know how mutable or immutable this memory is, so I don't know if defining a new one is the same effect as trying to rejigger one of these, or if it's more expensive. But right now, I don't really care. We can optimize it later. For now, we're just going to get it to work. So our resultant is the error plus the pure. And then we need to find our palette color that is closest to that. And so we will need a distance function. And then we'll need to identify the colors of our palette. And really, we don't even need a distance function, because we're going to treat each of the three components as independent, so we don't even need a three-dimensional norm. Because we're not going to use a specified palette, we're going to split each of the dimensions into a certain number of pieces. And for that, we're going to need uniforms. We'll have the default be 0 where it doesn't do anything. And then it's going to be how many levels for each domain. And so we'll have uniform int hue levels, uniform int chroma levels, uniform int luma levels. And so right, and here we're gonna output the resultant. Well, that's not right. How's this music bot work? There's a website called pretzel.rocks, and it's music that doesn't have any copyright issues. And so when I told it who I was, it just logs into Mixer in my chat and goes, hey, I'm currently playing that song. Okay, so what did we do that made it stupid? Let's put P here for pure. Make sure the pure still works properly. Okay, so pure still works. E should be 0. E is not 0. Why is E not 0? RG. Why is the Y? Why is the Y 1? What is going on in our squash shader? That our chroma is so very high. Like, wasn't it just green? Like, a moment ago? Wasn't it black? Okay, so let's do this. Okay, so why is that black? Oh, wait a minute. It's not the Y. It's the Z? No. I think there's something fishy about my my conversion algorithm.
Can you dig
Yeah, dyslexia can make programming fun and or frustrating. Okay, so why would 000 output green? Because that's basically what we're saying here, right? We're not. How about we just output the pure error? See what that's output. That appears to be purest black. I see the purest black. Purest black. Yeah, that is true. You do need to check everything forward, back, up and down, left and right. So if E is 000, why does doing that to it sometimes return green? This is maddening. Because we're looking for the error. The error is this minus that, which should be the integer part of the color that got passed in, which should be between 1 and 2. Subtract 1 should put it between 0 and 1. And should just be 0. Because here in Squash, all we did was make it between 0 and 1. Or between 0 and 0.5. Because we divide the hue by 360 to make it between 0 and 1. The chroma naturally is between 0 and 1. And the Luma is definitely between 0 and 1. So I don't know what it's getting so hung up on. This HM greater than or equal to 2 seems a little fishy. That's not the problem, but still seems a little fishy. So let's make sure the pure is still outputting properly. Let's go back in and figure out what the deal is with this 2. Oh, that's interesting. It is 2. Oh, because it goes from 0 to 6. Okay, never mind. That makes sense then. I don't know, the new Call of Cthulhu is real expensive. Like, it does seem like the sort of thing I would be into, but goodness me, is it expensive. Oh. Oh, it might be a floating point problem. It's probably a floating point error. How do we solve floating point problems? Because we cheat. We go the other way. I wanted to avoid using multiple floors, but like I said before, I'm not in it for the efficiency. I'm in it for making it work. Still green. Why is it so green? Yeah, because it does look gorgeous. And yeah, Cthulhu things need... It needs the dialogue, because you can't... Like, you can't get away with showing unspeakable evil, because you can't. Like, it just doesn't work. Skill system, interactive environment. Ooh, that sounds fun. Okay, so... There has to be something weird going on with my conversion algorithm. Ah, well, there's our first hint at something reasonable. But I like the Assassin's Creed franchise. I haven't played much of the newer ones, but I really like the older ones. Okay, shifting by 1 doesn't work because it might be 0. Right, shifting by 1 is a bad plan. Yeah, so it's the... Yeah, the voice acting, of course. That's why most games don't have it. So I had this figured out, and then it just left my brain. Because the top part won't be between... Oh, it's because I didn't add it during the squash. Because it should be between 1 and 2. And so if it's 0, it should add 1. Okay, so we save that to the squash, such that the unsquash can do the -1 to get the appropriate error. Well, we're doing slightly better. Oh, I didn't reload the squash. There we go. Well, pink is not the color we were expecting. Okay, let's turn off unsquash. Look at squash. Right, we squashed it too big. Squashed it too big. There we go. And now if we unsquash it, it's beautiful. That took way too much time. But it's good now. Our resultant is our input. Now we can do things in between. But first, we want to do quantization. And so we've got luma levels, chroma levels, and hue levels. And then we come down here to our resultant. And then we find which level is closest. So if our hue levels is greater than 0, if our chroma levels is greater than 0, and then if our luma levels greater than 0. So then we portion it off by how many there are. Good, that took too much time. That's how it normally works. Normally, yeah. But there are times where you're like, whoa, that went way too smoothly, given how many times you've had it take way too long. And so now we need to know whether or not GLSL has a round function. It appears to. We'll see whether or not that's true. So we'll save this, make sure it doesn't break it. So what we do is basically we multiply it by a number and then round it by that number. The trouble is I kind of wanted like having one level actually be fixed to just a single level. Such that if we set chroma levels to be 1, you can't have gray. You have color and black and white. But I'm not sure that really is ever anything that we want. Because even with 16 color, you're still gonna have gray. But I would kind of want it such that you could have a hue level of 1 as well, where it's just a single color. So I think I'm going to hard code that. Where if it's set to 1, it'll be 1. If it's 2, you multiply it by 1 less than that and then round. And so what we're going to do is we're going to have r.z equals r.z times luma levels minus 1. So at luma levels 2, it'll multiply by 1. And then it will round it. And then it will divide it by luma levels minus 1. So if luma levels equals 1, do a thing. Actually, that sort of a statement is annoying in shaders, so we're going to use this type. And so if it's 1, then you just return the maximum value. Well, the default value. I don't know what default value we should use for Luma, because it's never really a thing you're gonna be doing. So I'm gonna say 0.75, because 1 is pure white, 0 is pure black. I don't know what your average full color is. Like, full green would likely be 0.5? I don't know. Let's put it at 0.5. Call it a day. And so if the level equals 1, return 0.5. If it's not, return our scale up, round, and scale down. Let's see if we broke it. Hey, we didn't break it. Okay, we're gonna shaderify this even more. And move this into one of those as well. Okay, so save that and hope it didn't break. It didn't break! The reason it likes these better is because it can be done in one pass without any sort of branching. At least that's my understanding. Okay, so now, if we modify the Luma levels, it freaks out a bit. But it's kind of cool. Let's flip it forward so you can see how that works. So here we are at 6. 6 seems to make a bit of sense. 5, kind of okay. 4 is pretty weird. 3 is approaching the level of King's Quest, and 2 is just ridiculous. Like, that's King's Quest 1 level of ridiculous. But that's what we're going for. We want to be able to shift through different time periods just by selecting different values for this. And so I'm expecting to use like 6 or fewer. Two seems a bit crazy, but yeah. But we'll see what happens when we modify the other parameters such that you don't have as many hue and chroma choices as well. Because a lot of this still looks perfectly ordinary, even with only 6 Luma levels. That the background, because it has a gradient, looks weird. But if we go back to normal, like, there's some details that you lose, sure. But this does not... It doesn't look that different. And so if we just added a bit of dithering in this area, you might not even notice. Okay, so now we do the same exact thing for the chroma. we just swap out a couple of constants. Hue will be a little bit different because it's circular. But chroma, we should just be good to go. Default chroma. Probably be 1. Oof. That's a little intense. But again, by the time you get to 6, it's pretty much accurate. 5, it's all right. It's a little extra saturated, but that's okay. 4, 3 is rough. 2 is insane. And 1 is just blinding.
Are you ready?
Now, the thing with dithering is you would probably want to pick your palette more specifically than this, but this is going to be animated live. You can't estimate the appropriate palette every frame. You just can't. Like, even having an adaptive palette that tries to stay constant but has little modifications over time is still bananas. Okay, so now hue levels works kind of the same way, I think, but we want to be able to shift. We need to be able to shift 0. And so we're gonna need another uniform. Like, we need a uniform, float, hue, shift. Actually, let's make this an int as well. And make it out of 360. And so we'll do more or less the same thing. But we're going to have float HS equals hue shift over 360. We're modifying X. Okay, so what we're going to do is subtract HS from this. So that will do our hue shift for us. And then we'll add it back in afterwards. The problem is that this could be negative. Is that really going to be a problem? Shouldn't be a problem here. Will it shift it back to the correct place? I think it should. So let's save this. And we'll reload the effect. Ah, it's borked. Why is it borked? Because we got rid of a parenthesis. We closed a parenthesis too early? No. The real problem is... Well, no, because we're rounding it first, then dividing it, and then adding it. Did we forget a semicolon up here? No, uniform int hue shift. Float hue shift is hue shift divided by 360. All of that should have worked. Did we misspell something? No. So let's comment this part out, see if that fixes it. It does. And so we do it little by little. Find the part that's broken. Okay, so... that matches that end. This matches that end. Why is there a semicolon? No semicolons in the middle of statements. That's a new one for me. I don't often add an extra semicolon that causes problems. Okay, hue levels. One hue level. And so if there's one hue level, you return the hue shift. Which means if we up the hue shift, we go through the rainbow. Brilliant. Now let's get it such that you can see the brilliance. That's awesome. Okay, 2 levels. Aw, look at that. Okay, the problem is... oh, it's with this opening screen. We don't have enough things in enough colors. Okay, yeah, we don't have enough things in enough colors. But now you can see this color versus that color. Okay. Let's add another color. 4, 5, 6 colors. So... when working in 16 color back in the day, it would have likely been like that, roughly. Because you wouldn't have had this tan color in the back here. You'd have had a nice pure yellow, a nice pure light green, a nice pure dark green. I don't think you would have had this pink, though. I'm not sure where that's coming from. I think this feels more natural for the 16 color mode. kick it one more. This kind of seems like something we could work with. Let's see what we get with 5 colors. 5 colors is rough. Like 5 hues. I think that's what I'm supposed to have. I'm supposed to have 7 written. Such that it lines up at hue 60. Yeah, because we shouldn't have any change at hue 60 or 120. Yeah. So that's invariant to rotations by 1/6. Okay, so that's down to 3 and 3, 2 and 2. Yeah, I think we need to go 1 higher than you would think you would have. Well, that looks kind of cool. So this is more colors than you would normally have had, but that's fine. Okay, so we've gotten the quantization working, and just so you can see, if we up various parameters, we can get it back to normal relatively quick. And if we put Luma at 256, is that not enough? Oh, wow. Yeah, it's got more than 256 brightness grades in the back. $512 or so. 256 versus 0. Oh, it's got 256. 128 versus 0. Yep, 128's good. 64. Yeah, 64 is too few. But not by much. Let's check on chroma levels. 16 versus 0. 12 versus 0. Okay, so there is a little bit with 12 versus 0. But 16, hardly any difference. 32, barely anything. So, that's pretty cool. And so when working with the dithering, I think we're going to try to work from this point. So we're going to have yet another shader file. So let's kick it back to the code. I'm going to do a quick Google search to get the appropriate nomenclature. Diffusion. That's what it is. It's error diffusion. Okay, so we should probably do one of the simplest ones we can find. So we should probably do Sierra Light, because it is really quite simple. Requiring only 3 other pixels to get it done. So, we come back here, we copy unsquash, paste unsquash, and rename it to diffuse. And open it up. No uniforms well, 1 uniform will be necessary. We're going to need a repetition count. We're going to keep our... Actually, I don't think we even need these translation functions, because we're going to stay in the HCU space the whole time. We will need this, however. That's going to be a problem, because we would need to hit... We would need the hue shift in all of the propagations. So I'm going to design this without the hue shift at first, and then decide later if we want to include it. Oh, but it needs all of this information. So we might as well include it. It's going to have all of the same uniform settings as Unsquash does, because it needs this information to know how much error there is. So we're going to need this function in Unsquash such that we know they match. Okay, we reloaded the effect, and it still works. That's important. Okay, so... what do we do in the diffusion? We need to look at some other pixels, figure out how wrong they are, and then take that error into the pixel we're looking at. So we don't need any of this right now. For now, just return the basic color. And so what we're going to do is we're going to put it between squash and unsquash. Load it from file. Diffuse. It's currently just a pass-through, but we're going to need 7, 3, 3. And then the rep count for now is going to be 1. Okay, so we need to know where to find nearby pixels. So we need some example that knows the resolution of what we're looking at. Do, 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 do. OBS. Shader filter example. Let's try this one. UV pixel interval? That appears to be what we're looking for. Because that's telling us how wide any given pixel is. And this is where we currently are. Okay, and then for the Sierra light filter, we want to look at the one to the right, the one below, and the one below and to the left. Okay, so we want to check if this is less than 1, then do a thing, else do nothing. And so what we do is we compute the error and add it to our own error. Otherwise, do nothing. Will this crash? It shouldn't, but it does. Apparently it doesn't just like screaming into the abyss. So what we're going to do is we're going to set that to 0. And what we're going to have this do is do e plus equals that. Float 3e equals how we defined error over here, which unfortunately was relative to the pure. Do we need kind of need the pure as well, so we might as well grab these both. No, actually, we want E to be empty right now. Because each diffusion step... Wait. No. Wait a minute. What do we want? Because we need the error... We need the error from other points. But our own error that we're updating... Our new error should be 0. And so we'll likely make a function where we do this stuff. And then we'll just call the function a couple of times for a couple of different places. And a couple of different amounts. And so we need the difference between the nearest color and the actual color plus the error. And so we want P. Which way is the error pointing? Is it pure minus? Pure plus error? Okay, so it'll be that times the constant, which for this one is 1/2. Except we need the location. We don't want... Oh, we don't want our own error. We don't need our own pure. We need that information from the pixel that we're looking at. Yeah, because this will just look at where we are. That's not what we need. So we need to get this color. Okay, so this part, kind of big. What we need is neighbor 1 if this is true, do with it. So we get the neighbor color of that. float 2 of that, comma, dot y. That doesn't seem good. Welcome back, Manuel. So it'll be UV plus float 2 of this, comma, 0. Okay, we're gonna see if that crashes. It does. Oh, right, because we don't know vn.uv's type. What games will I stream in the future? I'm likely to play Dead Cells again. There are a couple of games I might want to go back to, like Mario Maker or Hollow Knight or things of that sort. The trouble is that all of the examples that I find tend to gloss over some of the finer details and just avoid others. Yes, I am aware that the new DLC is out. That's kind of why I want to go back to it, and I might want to start a new save file. Let me try image.sample, see what that takes. It looks like it should just take a 2D float. So what if we do this? This doesn't feel like it should work, but it might work. Does not work. Let's comment that out, see if that source of, not the source of the problem. How is that not the source of the problem? Okay, where's the source of my problem then? What did I do? I clearly broke something. What did I do? This? back to normal. Paste this in. See if this is the problem. Okay, that is a problem. Is just having it there a problem. Okay, so now is it the if? Not the if, so it is this. So let's start with that. Okay. vin.uv is some sort of variable, but what kind? Like, is it something that I can do something with? What is... Oh. Okay. It is expecting a float too. Okay. That dot x, that dot y. Totally works. Paste, save, and it works. Don't know how that's different from what I had before, but okay. Now, can we do this a nicer way, where we take this and then add this and 0 to it? We seem to be able to do that. Get rid of the if and return n1. Hey! We managed to shift it by 1 pixel. Brilliant. Doesn't seem like it should be brilliant, but it is. Okay, so we have N1, which is a color. What we want... Well, it's a squashed thing. So what we want is this, but for N1. We didn't get U. So it's x, y, z times 2. So n1 x times 2. n1 y times 2. n1 z times 2. Let's just define u. So we'll do that, save it, reload it. Hey, not broken. And yes, I do hear the music. I think I skipped agoraphobia the last time, but it's Halloween! Seems appropriate. Okay, so what we want is the error. So float 3 of C1 is P1 plus D1. I don't think we need to put that in anything, because what we actually want is the error, which is the nearest color to that. Subtracted from what color is actually there in the image. So as to diffuse the error outward, we're going to grab this error and push it to where we are. This right here will start like this. E1 will start off as 0. And so it'll just be the nearest color to P1, which will lead us to the error between P1 and just where it starts. That will create an error that we will then propagate other places. Now, this should be a function where we hand it these two things, and then it hands us this error back. And it's a certain fraction of that error. Okay, so what we're going to do is make a local C from that. Let's break this onto multiple lines so it's easier to see. Okay, so there we go. U equals C times that. P equals that. E equals that. Equals this. Return times frac. Did we break it? Of course we did. What's the trouble? There's a float 3. Oh, I forgot to tell it what I was going to give it. Float y x off. Actually, these should be ints. Int, float. Well, it's not the only problem. I got all of my semicolons. I called it the right thing. See if not running it saves me. Okay. Not running it does in fact save me. Turn float 3 of 0, 0, 0. Broken. Save. Reload. Fixed. So now we just go line by line and find our error. We found it. Oh, this is not global. So we have to pass v in into it. At least the UV part of it. Hey! We have a functional thing. Okay, so float 3 equals float of nothing. Plus equals that. You better be able to do that. Good. Whew. And then if dot y is good, then we toss in 0, 1.25. And then if that, wait. There we go. If that and x minus that interval is greater than 0, then we're going to do x of -1, y of +1, also 0.25. Save. Okay. Now the moment of truth. We need the pure and the error. Do we? It's probably easier that way. Actually, we just need the pure because we're going to add the error to it. But to get the pure, we need the u. And then we're going to say that the float 3r is p plus the error oh, we forgot to make sure the rest of it was okay. It is. Good. Okay. Okay, so our error is between 0 and 1, so we want it over 2 plus 0.5. So if the error is all zeros, we just add the 0.5 that we added over in the squash. If it's 1, it'll be 0.5. We add 1. Is that what we want, though? That seems problematic to me. P should also be over 2, because this pure has been multiplied. So pure over 2 gives us between 0 and 0.5. Man, I'm getting myself confused again. Okay, it's not plus. It's times. Is it? Why do I always need to get myself confused in these things? So, if our error is 0, what do we want to add? We want to add 0.5. If our error is 1, man, I don't think I thought this through. Because by dividing by 2, all I've reduced it by is 1 bit. And so we don't have enough room for the error. Because the error can either be there or it cannot be there. We only have 1 bit worth of space for the error, and that is not enough. We need more space. Okay, let's set these to... that's the wrong one. Unsquash. Set them all to 0. Still looks perfectly fine. Let's make sure that it's actually running my code. I'm not sure it is. Oh, because I didn't reload squash. Okay, we've run into the same problem we had before, but that's okay. We kind of figured out how to do that. Thanks, Mac. It's not doing much of anything that it's supposed to yet. I hadn't realized how little space I had afforded myself. Okay, so over here. What we put in is each of those things divided by 256. Over here, we multiply it by 256. Pure is the fraction. Error is the rest. Divide by 256. Oh, that's cool, but wrong. Let's work with a smaller constant to make sure we aren't just completely borking ourselves. Do I know what I'll be streaming on Friday? I don't know just yet. Sorry. Okay, so we're putting in this over to... Oh, right. We need to reload both shaders. Always reload both shaders. Well, that's fascinating. Oh, that's interesting. We're starting to get some artifacts. At 8. Why am I testing it on the Stardew Valley menu? Because it's got colors, and it's more interesting than other random things that I would have laying around in, pretty much anywhere. I mean, I could go into the game itself, but meh. So divide by 8, we're seeing some artifacts. Let's do by 16. Well, that's some serious artifact right there. How did that happen? it's interesting how so much of it remains unchanged. But then that stuff gets hit really hard. The brightest whites in the cloud get really confused. So we don't have nearly as much overhead as I expected. I also wonder, can you just simply bit shift things? Seem to be able to. Oh. Why did that break? It was fine just a second ago. Okay, fine. It's also bit shifting the wrong way. Nope, broke. Okay, so the question becomes, will 3 bits really be enough space for propagating error? Doesn't really seem like it should be. Well, it's a shame I didn't actually get to implement this. Just because I can't wrap my brain about how to hide the information in the upper bits. Okay, so what we have here is between 0 and 1/8. And what we have here, we would need to hide in the upper 3 bits. So we need to have this be of 3-bit resolution, roughly. I think that's how this would work. Because, for example, if this P was 0 to 255, it would be 0 to 32. It would go from 8 bits down to 5 bits. And then if this were then from 0 to 7, we would want it to take the space of 32 to 255. Is that right? It doesn't seem right. No, because we're adding something that shouldn't be added. Because if it's 0, it should just be 0. And sometimes I just stare at a problem too long. And I should just turn off the stream and just actually take some time, have a crunch bar, and really think about it. Because we'll end up dividing the whole part by 7. To get the error. So this error would be between 0 and 7. Man, my brain is just not picturing this well. because I know you can do this. But I've never had to do it before. And I'm sure it's dead simple to anybody who's actually done it before. So I suppose we could just do it in base 8. And so it would be the basic thing plus 7 times the error divided by 8. There are 8 parts. 1 of them is this. 7 of them is that. That should be right. This part is not right. It should be divided by 7. Should it be divided by 8? It should be divided by 8. Okay, let's see if it just works. Doesn't seem to be broken. Doesn't seem to be doing anything, but it doesn't seem to be broken. Because we're returning C instead of R. There we go. Okay. Diffuse does not seem to be doing anything. So I don't know if we're not getting any from or if we just don't have enough space to propagate a significant amount of error. Or if the effect is too small to be registered with just one copy of diffuse. But you should see some change. Okay, so let's force something interesting. So let's actually diffuse some like mandatory color error. Oh, it's black. Did I never reload diffuse? Think I broke it. Because I never reloaded diffuse. Okay. Okay, so let's return P over 8. Not working. C. C is fine. Why not P over 8? Is it just P? No, not just P. U over 8. Because they're float 3s. Float 4 of Rx, Ry, Rz, 1. There we go. Ah. So it's changing a little bit, but not in a good way. Just kick the white to black. That is not what it should be doing. Seven, 3, 3, 2. And we should also be sending in things that are divided by the rep count. Yeah, it's doing a whole lot of nothing at this point. So I don't know. I don't know whether or not it's what I coded it to do that's wrong, or whether or not I miscoded part of it. But it looks like I didn't have as much headroom as I expected to be able to pass along the error as it is. When did I start playing Stardew Valley? I don't know. It's been quite a while. I started playing it not too long after it came out, I think. Yeah, I was hoping that this would have enough headroom to pass the error along with the original color, but it appears to not have any extra room. And that's a shame, because I really wanted to try this technique, but it doesn't work if you can't pass things along. I wonder if I could quickly make an ordered dither. Shouldn't be that hard, because we've got a lot of tools already in place. So we've got N color. What is this called anyway? Bayer matrix transformations. So Let's give it a shot. Copy, paste. Fair dither.shader. So doesn't need any other pixels to get the job done. It does still need all of this for the nearest color. But it needs alternatives. So let's take a look at how it computes this nonsense. Okay, so takes a number between 0 and 1, subtract 1.5, multiply it by a shift value, add it to current part of so it would shift all three components. By the same amount. And so we're not working strictly with the nearest color. We're going to work with the nearest color and shift it by the value from the matrix. Okay. And so we'll probably just stick with 4x4, so we only need 16 of them. I don't know how to make GLSL do the bitwise operations to be able to construct the matrix itself. And so I'm going to need to make it do it itself. So what we need is the X index. So it'll be v in dot uv divided by that value. We need the y index. Y index. Why not index? Okay. And then we take them mod and mod the size of the matrix. So int x mod equals mod of x index comma 4. Okay, so we should be able to save this. Go in here, remove our dead filters. Add our new one. And it's broken already. Because we're returning the wrong thing. Let's go. Borked. GLSL mod. Should just work. It's computed as x minus y times floor of x over y. Turn x minus y times floor of... Is it x over y? Yeah. Oh, right. It should take floats. And ints. No, it should take 2 ints. Okay. Okay, we do not need any of these uniforms. Okay. Now that we have that, then we pull from a matrix a particular value. So, if mod equals 0 and y mod equals 0, so this is just a factor. So float of factor equals 1. And then elif? Elsif? Let's try else space if. We could probably do this with nested ifs. This is the worst way to do arrays, but I don't know. Actually, GLSL array. Can you make a two-dimensional array? You can totally make a matrix. How do you define the matrix? Actually, we don't know if you can do that. So let's check real quick. Mat for factors. Broken. I didn't think you'd be able to make that. So this is real ugly. We can do this better. Zero 0.5. 1/8. 0.125. And then 5/8. So we just multiply this by 5. We got 5 at the end. Carry the 2. Carry the 1. 5/8. Pretty sure that's 5/8. And then we'll need 1, 2, 3. Actually, we could just write it like they have it on the Wikipedia page. 8 to 10. Over 16. 12, 4, 14, 6. And so 3, 11, 1, 9. And then 15, 7, 13, 5. 15, 7, 13, 5. And so then can we use matrix note, like array notation for this? Should be able to, yeah. Oh, we didn't break it. Still not broken. 2, 3. Okay, so now we have a factor. What is their definition of big N? Big and evenly chosen colors. Okay, so that'll be different for each of the things, but we'll have factor minus 0.5 times our thing plus the current value. So I think we should just pass the factor into n color. And then deal with it in here. So we find the nearest color to our current color, and then we use this factor to shift things around. So that will shift this right here. Plus factor minus 0.5 times however many things per number of intervals. Well, number of colors. So hue levels minus 1 divided by, so 1 over the number of hue levels, because it was working with 255 in the example, but we're on a scale from 0 to 1 here. And so instead of multiplying by that, we can just come over here and divide. And then we subtract the offset. And then we add it back in. So that should just work. So here we add some parentheses, put this in, and instead of hue levels, it's chroma levels. And then we do the same thing here. And we broke it. Because of course we did. And color. Why you always gotta be a float 3? C is a float 4. So pass in C dot RG XY. Wait a minute. We never made it hue saturation value. Or hue chroma-luma. We're gonna need that. Okay, so Pascal XYZ should be fine. Factor is afloat. Oh, it works now. Why does it work now? Oh, I don't have any of the uniforms.
Push me down to the ground. What goes around comes around. You won't put the flame out. You can't get to me. Say what you wanna say. Go take it all away. But I'm here to stay. No, you can't get to me.
HCU to RGB of float 4 R.X, R.Y, R.Z 1. Well, well, well. we go. Good old-fashioned dithering. It's nothing new, but it is something old. Yeah, when it's down at 2, it's too bad. But at 3, it's kind of okay. That's neat. With a spooky filter on it. And whether you put the spooky on before or after. That's cool. Let's see if we get any... That's neat. Okay, let's load a game and see how it looks. Let's actually close it up and go into the game itself. It's pretty bad. I'm pretty sure we need to go to at least the 8x8 if we want it to look okay. The 4x4 is just bad. Let's see if anything could fix it. Yeah, because if I put it up that high, it's got too much color accuracy. Like, it's got too much... It's got too much hue and chroma accuracy to really feel like a dither. And now it's too much red. Like anything that's kind of red, it really redifies. Yeah, now it just looks bad. I mean, it could be okay just to add a little bit of noise, though. Like, maybe put them all at 9? I mean, it does feel a little bit more like a TV now. Maybe put them at 8? Oops. That is kind of interesting. And what happens if we swap the order? Makes it oddly green. Yeah, I don't know. Let's kick it back up because it looks better pre-spoofed. Okay, because it's 7 over here, it starts looking bad. Let's head into town. I think town might be the most interesting place to see. Okay, so let's kick it up by 1 each. Okay, and then 1 more. Yeah, Luma seems to have the most effect. Yeah, because the color mostly affects, like, really the red. The red is the most effective. Hey there, Mac. Yep, we've got the dithering up and running. It's not the algorithm I wanted to write. We didn't have enough headroom for that one. So I just did a standard Bayer matrix ordered dither. And so with 8 intervals on each of the parameters, it it's pretty subtle. Like, on a lower resolution, you probably can't even see it. But at full resolution, you can kind of see that it changes the texture a bit and makes it look a little more television-y. But if we kick them down, here we are at 7 intervals each. 6. 5. 4. 3. 2. Like, 2 is really intense. Like, this is not how anything should ever be. Three at least gets you all of the major colors. 2, it's just like, no. But you'd expect at least 6 for the color. But then with the chrome and the luma, you're like, maybe I don't need as much. But you kind of do. Like, it gets kind of sketchy. And so if we kick them up to 6 each as well, just to match the level of the color, it's kind of okay. The mesh is still a bit intense. But yeah, again, if your bitrate changes, then you might not see it at all. And so I was thinking, if the dithering worked great with a non-stationary algorithm like this one, where it did a better job of dithering, it would reduce the number of colors, and then it might be able to compress it better, such that it would actually work better for the stream, such that you didn't need as much bitrate. But this sort of ordered dither doesn't really help anything. And, like, here's it on, off, on, off, on, off. It really would only be for me. It was fun to program, and it was fun to see how my other idea just would not actually work in this setting. If I were writing a program where I was doing all of the stuff, then I could probably have it dither just fine using any of the standard dithering algorithms. Could even parallelize it using that one guy's paper. But for a shader where it only really knows itself, you don't have enough data pipeline to make it work. It's a shame. So that's okay. I really did want to just play around with the quantization, and the dithering, just to make sure I understood how it worked, make sure I was able to implement it, have something to program that wasn't super crazy frustrating. Well, the thing is that the trouble with this retro is that it has large pixels, but they're not offset consistently. Like, you've got sub-megapixel positioning. And so I can't have a shader that knows how big these pixels are and only dithers by those large pixels. So you would need to be part of the game and know where these lined up to be able to do anything with them. And a shader's just not gonna do it. I mean, maybe it could. Maybe it could, because you could look at the pixel next to it and see if it's the same. But then what if you've got two in a row that are the same color? It wouldn't really know. I'm not sure it would need to know in those circumstances, but still, there are a lot of fiddly little details. What is this? Oh, it's just a sign that says they're closed on Wednesday. But yeah, I think I'm gonna get going. I've got some chocolate waiting for me. Yeah, you can't get away with that in shaders. You need to do a very minimal amount of things. But yes, I'm gonna get going. There are crunch bars waiting for me. Good night's sleep waiting for me. And then a bunch of classes tomorrow. Yay! I will post a thing on Discord regarding what to play on Friday. I do plan on playing it with this fancy spooky shader set, even though it won't be October anymore, because I kind of like it, and I might make it my thing. So if you're watching this right now or in the VOD, feel free to head over to the Discord and say, hey, I want to see, and then insert game there. We could play Mario Maker with this spooky filter. We could play some more Dead Cells. It's been a month for me to get rusty. Pretty much anything I have, I would kind of like to play, because it's been a month since I played any games. Well, aside from Stardew Valley on Tuesdays. Regardless, I will see you in the next live stream or video of Stardew Valley, or Binding of Isaac, or Mario Maker, or Dead Cells, or who knows what, with light.